I actually made some notes.
You don't need to. No, like not the bottom ones. Those are for me.
Yeah.
All right, ready to go.
Sure.
Wait, Chris. Count it down, my friend. Oh, shit.
That's a bad way to start. Good morning, everybody. My name is Vincenzo Pasquantonio, and I'm happy to kick off episode 2 of TechTime with Tanmay. We're broadcasting today from the IBM Canada Lab, our Markham site. Today's topic, we're talking about high-performance computing in the cloud. Just a show of hands for people in the room. How many people know what high-performance computing is? 1, 2, 3, 4, 5. All right, I'm going to say about 50%. So I spent a little bit of time in this space. In a nutshell, high-performance computing is a way to take large mathematical calculations and workloads, distribute them to large server farms in a way that's as efficient as possible and can increase speed and time to value. It used to be called grid computing, distributed computing. It's a pretty interesting space with some really cool use cases. So think of healthcare, genomics, personalized medicine. Think of oil and gas and precision drilling and mining. Think about automotive simulations. Think about now weather forecasting, right? As we talk about weather industries and stuff like farming and stuff like, actually, we had a cool use case the other day where we talked about predicting intake into hospitals based on weather forecasting data. So at the end of the day, all of these use cases boil down to the huge mathematical calculations that need to get farmed out to large server farms in a way that you can get results as quickly as possible. And this is the essence of high-performance computing. I want to give 2 shameless plugs to IBM here. Number 1, check out top500.org, right? If you're a HPC geek or just a geek in general and you want to see what the fastest, most powerful computers in the world are, top500.org is the organization that tracks this. IBM has the top 2 in the world at the moment, Summit and Sierra. Second plug, IBM acquired a company called Platform Computing right here in Markham, Ontario, about 8 or 9 years ago. And I was fortunate enough to spend 8 years of my career with them. And they focused on that thin layer that takes all of this workload, distributes it out to these server farms, and returns results. And it's a workload management layer. I'm going to leave you with my favorite use case on high-performance computing. It comes from a customer called Red Bull Racing. Everybody know Red Bull Racing? Very cool use case. So Formula One actually regulates the amount of time you're allowed to test your race cars on a track. And the trend has been that they're giving you less and less time because they want the sport to be more competitive, right? The longer time you have to test your cars, the more perfect you can make them. They want that sense of randomness or that sense of surprise. So they're actually shrinking the amount of time that these Formula One race cars are allowed to test on test tracks. I was just reading last night, they're down to 6 days. So you have 6 days to test these Formula One cars. So what companies are doing, and Red Bull was one of the first, is they're using HPC technology to actually run pretty sophisticated simulations outside of the racetrack using computer simulations to be able to optimize and refine their cars so they need less time on the track. And they're an IBM customer running on IBM hardware using our Spectrum computing technology. So 2 things I want to hear today that I see as the future of HPC. And actually, maybe I'm priming Tanmay with a few questions here, is the convergence of HPC workload and AI workload and how the industry is going in that direction. And also how quantum computing we're going to play a role in the future of HPC technology. So with that, I want to introduce Tanmay. Tanmay, come up here, episode 2. And another shameless plug for Tanmay. What I like about these series is that we're focusing less on marketing and popular opinion and more on expert opinions in technology. So I hope you guys enjoy this episode. I'm going to hand it over to Tanmay, and best of luck.
Thank you very much, Vince. I've already got a microphone.
Perfect.
All right, thank you very much. Hello, everyone. As you know, my name's Tanmay Bakshi. Thanks for joining the second episode of Tech Time with Tanmay. Today, we're going to be talking about high-performance computing technology. Now, as you may know, artificial intelligence technology, machine learning is the kind of tech that I focus on most. And a lot of this technology and lots of other next-generation technology today are pretty dependent dependent on something a lot more fundamental. And that fundamental technology is, of course, high-performance computing. Now, today, with next-generation technology, the needs from the world of hardware are really increasing. And high-performance computing technology gives us an effective solution to actually use these next-generation technologies and enable them to solve problems. But there's a bit of a problem with the field of HPC. And it's that it's really difficult to use. It's traditionally been, large, like a ship that's really slow to turn. It's been difficult to leverage the world of high-performance compute because a lot of your attention goes to the world of compute infrastructure instead of actually solving problems on that compute infrastructure. And so this brings me to our special guest today. Now, it's kind of hard to introduce today's special guest, and the reason for that is because 10 years ago, as you can imagine, cloud computing technology is in its infancy, right? It's barely evolved. It's barely even started. And still, this visionary, today's special guest, he had this idea. What if we were to get the best of both worlds? What if we could take the world of high-performance computing technology and get that effectiveness, but at the same time, get the agility and the speed of cloud and put them into one single package? And so, in order to actually achieve that vision, he founded Nimbix. Now, Nimbix, for the past 10 years, has been providing high-performance computing technology in the cloud. They're doing it in some really fascinating ways, providing all sorts of exotic architectures and domain-specific compute platforms on a single cloud environment. You can get IBM Power AI systems, you can get FPGAs from Xilinx, all sorts of things, all on that one compute environment. And so now, without any further ado, it is an honor to introduce Steve Heiber, the CEO of Nimbix, my mentor, to the stage. Thank you very much, Steve, for joining in.
Thanks.
Thank you.
It's great to be here. It's great to be here.
Thank you very much. As a matter of fact, I'm really glad because this is Steve's very first time in Toronto, and the fact that he came here for TechTime is really fascinating. So thank you very much once again, Steve.
It's great to be here. A little chillier here than from Houston, Texas, where I live, but it's great to be here.
Thank you very much. So how about we start off with a bit of an introduction, right? So let's talk a little bit about Nimbix, what it's about, and what exactly Nimbix does.
Sure. Well, I think you gave a great introduction in terms of setting the stage for who we are and what we do, and that is that this notion that high-performance computing, which has been out of reach for many over many years of its history, right? Supercomputers that were monolithic and lived inside of large enterprises, government labs, academia, but this idea that more and more industries are going to rely on it because our computational needs keep expanding.
Yes.
And so we need to, create pathways for innovators to access this in much more efficient ways.
Yes.
The other piece behind sort of the beginnings of Nimbix was this notion that architecturally, the ways that we have done computing historically with CPUs getting faster each generation, that's sort of slowed down through, you've heard us talk about Moore's Law, and needing to have purpose-built architectures. And so we introduced this notion of accelerated computing to bring new hardware to these environments and then make it available as a public cloud so that anyone from startups to large organizations can use it.
Absolutely. That's fascinating to me. I mean, as you know, at IBM, we work on like all sorts of next generation technologies, AI, machine learning being one of the prime focus sort of areas. And specifically, I believe artificial intelligence or machine learning, that was one of the first sort of major use cases where we've seen that we've had to use specialized hardware in order to achieve the goals that we want to achieve. Like, for example, CPUs no longer suffice, we need GPUs. Yes. GPUs no longer suffice, we need TPUs and these custom processors. As a matter of fact, if you take a look, nowadays there's this new company providing these things called Grok AI inference chips with things like deterministic latency and all sorts of next generation stuff. And where can you find these chips? You can find them on the Nimbix cloud.
That's right.
So that's really fascinating stuff. Now, really quickly, before we get deeper into the technology behind Nimbix and what it enables people to do, a question that I had for you was 10 years ago, again, when Nimbix started, cloud computing was in its infancy. So how did you come to the realization that it would be great to get the best of both worlds for HPC and cloud? And what were some of the challenges that you faced because you were so early in the industry, because you were pioneering this tech?
So what's interesting is before Nimbix, I was at an FPGA company called Altera, which many may be familiar with. They were purchased by Intel a number of years ago as a reconfigurable type of device. And one of the things that we were working on in the compute side of it that I was involved with was computing using these chips to accelerate processing tasks by 100-fold. And so I thought that was really interesting. And but it was difficult. They're difficult to program at this time, and that's still an area that we're continuing to innovate, is making them easier and easier to onboard into. And so at the time, cloud was still very nascent. And the idea was, what if we could hide that and simply provide an interface where you could blast a workload into this infrastructure, let it do its magic, give you your answer back 100 times faster. That was just the general idea behind it. And so we started looking at what was available in the market. And at the time, it was really AWS. And Microsoft Azure was still very Windows-centric in its cloud. So it was very early days. But it was virtual machines that gave compute agility. The virtual machines were built to allow people to spawn up machines on demand and elastically, which was extremely exciting. But the limitation that they had at that time was performance, right? And so a lot of folks that were involved with high performance computing said, it's just too expensive, the performance isn't there. So we, basically said, let's go tackle that problem. Let's solve the performance problem. Let's go introduce capabilities that allow that to be used. And now we're seeing across all of the major hyperscaler clouds the introduction of higher performance systems to help solve for this need.
That must be really, really fascinating for you to see that the solution that you envisioned before Amazon or before Google or IBM Cloud, before Microsoft Azure, before all of that, they are now recreating solutions similar to Nimbix's, right?
Yeah, well, I mean, I think of course, it's nice to see that the market is arriving, and I think those are some of the challenges in the early days were just helping educate this need, and it was because it was still emerging.
Yes.
And I think that now we're seeing that those use cases proliferate. Now, I will also say that there were customers who had the need, but if you remember in the early days of cloud, there was always concern, security, moving sensitive workloads to the cloud, those kinds of things that are still very real issues today. But as it's become a viable pathway for enterprise computing to adopt cloud for high performance computing, it's really opened up the market, and that's why you're seeing more players, offer capabilities here to help customers, solve these problems more efficiently.
Interesting. I mean, when cloud computing was in its infancy, I was only a couple of years old, so I can't attest to that. but yeah, that's absolutely fascinating to see how things have evolved from here and how more and more people are starting to create platforms similar to this. And what I'm particularly interested in are use cases. So Nimbix's platform, what are some things that Nimbix has enabled people to do that either A, couldn't have been done without Nimbix, or B, would have been much more difficult, would have had slower iteration times, or wouldn't have enabled developers to do what they do, solve problems, without that power of Nimbix?
Yeah. There's a couple of things. So first, we built some underlying software technology that we call Jarvis that powers our infrastructure. So we built our own infrastructure because it's purpose-built. It's basically a supercomputing architecture. And Vince mentioned at the beginning the number 1 and 2 supercomputers are these IBM machines, and we have the equivalent running in our cloud, clusters of these. They're actually slightly spec'd a little bit different. But the point is that it's a supercomputing architecture under the hood, which gives us performance advantages and shortens time to results. And oftentimes it will run at the same speed as on-premise supercomputers because it's running unfettered. And so the technologies that we introduced to achieve that were a couple of things. We invented this capability that we call reconfigurable cloud computing. And it's this idea that the point of entry into the cloud is not launching virtual machines. It's sending a workload that defines the data, the type of compute you may want, and any parameterizations for the execution environment or the application. So whether you want to run your job on one machine or 150 machines or 1,000 machines, it's one element or parameter of the API call, and the system takes care of all the configuration of the machines. Spin up, tear down, completely solves that problem. So that's one technology that we developed to create really what I would refer to for the benefits for the customers, ease of use. We take out a lot of complexity from cloud for onboarding work. And then the second important technology is around containers. And while that seems like, well, yes, everybody's talking about containers these days, back in 2012, they weren't. The reason why we picked containers was, again, for a very specific reason. One is to get the same agility of a virtual machine without a hypervisor, but unlock the performance of the underlying infrastructure. So we want to allow all of the native processing horsepower of these machines to go straight to the application unencumbered. And containerization was the mechanism, the technology that we could use to do that. And so as one example, when we pioneered the use of FPGAs in the cloud, there was no virtualization component stack for FPGAs inside of a hypervisor. And so using a container allowed us to present that hardware to the application unencumbered. And so so think of the first one as technology to enable ease of use. Second one is a technology to enable performance and agility.
Very nice, very nice. And of course, there's advantages and drawbacks to everything, right? So like, for example, if we take a look at IBM Power and how Nimbix provides Power AI machines, and of course through containers, as you mentioned. Sometimes there's some things that you can't do in containers, like for example, changing SMT modes, right?
That's
so like currently by default, it's I believe SMT4 on the AC922s,
correct,
which you cannot unfortunately switch. But then again, the agility that you get with being able to just spin up a machine, run what you needed to run, and get your results right back out is unparalleled. And so that's truly an advantage of that platform. Now, I know that Nimbix has given above 400 million hours worth of compute time, right? That's 400 million hours worth of compute. And I also know that Nimbix has served customers in 68 different countries. That's a lot of compute that Nimbix has provided. And so really what I'm wondering is, sure, the technology behind Nimbix is great, but what kind of impact does that technology have on society? And really quickly, before you answer that, one more thing I wanted to mention for everybody joining via the live stream and everyone in person as well. Any questions, we will be taking them towards the end of the session, so feel free to put them in the chat. We'll take a look, or in the amphitheater, we'll get a mic to you and you can ask. But yes, impact on society.
Yeah, well, I think the numbers, I think even are exciting because of the reach, right? And when we talk about reach and we talk about democratizing access, it's giving these advanced capabilities to any kind of user, right? Any kind of developer, any kind of innovator who needs advanced computing horsepower. And so I think that's a really key attribute of cloud, right? HPC in the cloud is that you can get this power in the hands of many, many people. And I think for me, that's about solving these meaningful problems. And so how does this help? I mean, I think from my perspective, how does this help the world? How does this help our community? It helps us solve really meaningful and really challenging problems. We read every day in the headlines about weather, climate, drug discovery, medications, innovations in healthcare, even things that are creating optimizations are really important. And so these are all innovations that platforms like Nimbix and high-performance computing in the cloud in general help deliver in a much more rapid fashion.
Absolutely.
And as our population continues to grow and we have to tackle these problems, we need to keep propagating this horsepower and helping us bring these innovations to market much more quickly.
Certainly. I mean, you may have heard of a project that I've worked on. This is a project that I've worked on quite closely with Nimbix, actually. It's in the field of biometric authentication, where the idea essentially is, how can I create sort of like a next generation system for biometric authentication that identifies you based off of the way your heart beats? So via electrocardiogram, based off of the electrical activity of your heart. And that's something that requires complex deep neural network models. This is something that's not easy. There have been models that have been used in the past, but they're simply not robust enough to be able to work in real world scenarios. And without the agility of a platform like Nimbix, training these models is very very expensive and very, very time consuming, because then I'm not spending my time saying, how can I build the best model? I'm spending my time saying, how can I actually get the compute infrastructure in order to solve those problems?
And if I can say just a point on that, and I think it's you know, historically we've had developers who are solving problems, like for example your Heart ID innovation, where you could get the resources, try to get the resources, but to your point, it was very expensive. Sometimes it was a lot of friction, right? How are you going to provision that system? Where's it going to live? Who's going to actually power it up and cool it?
Yes.
Where the software stack? How are you going to actually put together?
Logistics.
So those are elements that create friction and barrier to the innovation, right? It's time, takes longer, and the cost is higher. So the notion with what we can do in the cloud is we can compress that. We can bring those innovations to market much more quickly and much more cost effectively. And that just spreads the ability for folks to innovate in a much faster rate.
Very nice, very nice. So I mean, sort of expanding on these use cases a little bit, I want to see some sort of actual problems that Nimbix clients have solved. So do you have any like case studies of different companies solving problems with Nimbix?
We do, and we actually have a page on our website where we outline several of these customer case studies, white papers, areas that we've explored together with our customers. But for example, Maha Systems brought to market a millimeter surface mount, millimeter wave antenna. So the problem that they were trying to solve is rather than using traditional planar antennas, and these go on like autonomous vehicles, data center applications where you're doing gigabit data transport across these little antennas. So you have to simulate the dynamics of electromagnetic waves, and it's very computationally intensive. And so to be able to bring a new product like that to market would normally take years, and we were able to help them compress that time to 12 months. Another customer in a completely different industry called Minnow Marine built a entirely new hull design with self-elevating towboats brought this whole boat design to market in less than 12 months. Wow. And so again, these are things that in an industry that has a certain way of doing things, that we can introduce disruptive capabilities through the use of high-performance computing. I think in the area of agriculture, U.S. Department of Agriculture has, and I think Vince mentioned, genomics, bioinformatics, doing genome sequencing and annotation and so forth is very computationally expensive. And so we've worked in Agricultural Research Service to help them actually study food supply assurance, for the well-being of the citizens of the U.S. So those are really important, areas where customers have used us.
Fascinating stuff. Now, so of course, customers have been using Nimbix for all sorts of great stuff. But what I'm interested in now is the technology that actually enables Nimbix to work. So, I mean, again, especially the fact that you started so early in this industry and sort of pioneered this whole HPC in the cloud thing. What were some major technological challenges that Nimbix had to overcome to create this platform where you could so easily use these exotic architectures and different kinds of compute?
I think that the first biggest challenge was really tackling taking a non-virtualization approach to cloud, right? That was pretty much the de facto, still is today. And there's nothing wrong with virtual machines other than from the perspective of high-performance computing, to the extent that there's a layer that affects performance, we want to untether that. So that was very important as we built architectures that use things like GPUs or FPGAs. We needed to be able to deliver that to customers with the same agility as a virtual machine without it being in a VM. And so, really building the stack that enabled us to do that was one of the important barriers that we worked to overcome.
Yes.
I think the other one that's gotten a lot easier is in the early days when we were using containers. Just very few people knew what containers were. Many of our customers don't even know or care. They're using the applications that run in a container to do their science or do their math. And so that innovation in and of itself, in a time where the de facto industry method was virtualization, was there was friction, right? There was skepticism. It's not a technology that can work. For example, SMT versus non-SMT. There are some limitations or trade-offs that you make. But in the end, what it delivers is incredible performance and incredible cost per result economics. And to me, that's a really key attribute in HPC cloud, is how do we reduce the cost per answer for a scientist and an innovator to bring their products to market? Because that's how we're going to get more products to market more quickly.
Exceptional. Yeah, you're right, absolutely. I mean, I've always believed that developers solve problems, and when you provide them with the infrastructure to be able to more quickly iterate, they will solve problems faster.
Yeah.
And as the world's problems become more and more complex, we need more and more complex technology, we need more and more complex compute to power that technology.
Yeah.
Which brings me to exotic compute architectures. Yeah. Now you mentioned FPGAs, we've talked about power a bit. So I wanna know what your thoughts are on why these exotic compute architectures are important for the kinds of technology that we use today and how it's gonna affect the way we work in the future.
Yeah. So I guess I'll first say that these are my views on the use of what we call heterogeneous systems in compute, different architectures for different types of workloads. I would think it's fair to say that there's still debate, in the industry about what are the things that ultimately sort of rise to the top. But I'll tell you a few of the undercurrents that have really driven that from my perspective. And having started in the semiconductor industry, we have this notion of shrinking, the transistor size to fit more transistors on to run faster. And for 50 years, we would double the number of transistors, deliver more performance. The HPC #1 system, 1 year, it was whoever deployed the latest system that got the faster chips had the new #1. As we've gotten to the edge of the physics, and we're still a few ticks away, we get into the low single digit nanometer, 7, 5, 3, you're at the atomic scale, you're sort of at the end. So what that means, and this may be, in the Q&A period, we can touch on, quantum, Vince mentioned that. But from my perspective, what it means is we need to figure out, if we have a canvas of transistors that can't get smaller and we can't make them go faster without burning up the chips, let's rearrange them to solve certain problems the most efficient way. NVIDIA happens to have taken a graphics chip that's really good at vector processing, really good at now with these tensor cores that they put in hard IP in the silicon to do very well at inference or at training, right? You have an FPGA that can actually be reconfigured to do video acceleration or video transcoding real time, and then maybe even add AI inference in stream real time. So these are capabilities that you just can't do in a general purpose architecture. And so, my view is that as we, we conceive of new workloads in this area, we're going to continue to need purpose-built architecture. So that's my long-winded general view of it, but we can now, if you want to double-click on any of those.
Yeah, absolutely. I mean, that's really fascinating stuff, what you mentioned there. I completely sort of agree that as we reach the limit of the performance we can get on general-purpose chips, we need more and more specialized hardware. And I believe that sort of the highlight sort of technology that people put on HPC, right, is AI, machine learning technology. That's sort of like the de facto standard of, when you think of HPC, the first thing you probably think of is AI, ML, and then there's a lot of other technologies, of course, that are very, very important, but sort of the one that's most popular, the one that looks nicest, would be artificial intelligence technology. I mean, Vince was also mentioning, right, that we're starting to see sort of the convergence of artificial intelligence, machine learning teams, HPC teams. What are your thoughts on that? Do you believe that artificial intelligence technology is important enough to deserve first-class support in things like HPC? And one more thing I want to mention really quickly is that lots of companies have been doubling down on this. Like, for example, Google, right, with Swift for TensorFlow. They have proven that they believe that machine learning AI technology is important enough that, hey, we should be creating first-class compiler support for TensorFlow. So what are your thoughts on that? Do you think it's important enough?
Absolutely. I think it's a convergence that's absolutely happening at a rapid pace. And what's interesting about that, just historically, Nimbix had adopted an accelerated compute mindset, right? Where we're going to have infrastructure that supports these types of acceleration technologies, GPUs being one of the earliest that we supported. But at that time, we didn't have deep neural networks running on our cloud.
Yeah.
We had real-time ray tracing. We had, computation, vector math that, could be accelerated, X% higher than a general purpose CPU. So it was fascinating when, the popularity of deep learning and AI that demanded GPUs sort of landed in our cloud. We didn't sort of forecast that. We didn't, we're happy that we were well positioned for it.
Yeah.
But I think that what we've seen in our enterprise customers who have traditionally been HPC, that is a line of business, right? Oil and gas, finance, a lot of organizations require what I would call traditional HPC for their science. Then you add in the domain, whether it's for their business reasons, for the science itself, AI and deep learning, you don't want these from an infrastructure standpoint to be siloed because a lot of the attributes of the infrastructure are the same. And so it makes absolute sense to converge those into a single platform for computing that can equally well handle traditional HPC and deep learning and AI processing capabilities.
Totally. That makes total sense. With artificial intelligence, machine learning being one of these most important next generation technologies that we're working with and being so widely applicable across domains, it does make sense to sort of have them converge and see where collaborations can be made better.
Yeah, and just to, you mentioned Google, but we're seeing that in many of the technology companies that are providers in the space, from hardware OEMs to the cloud providers, where they are converging those business functions. You're now seeing leaders that are HPC and AI in their titles, right?
Yes.
And they're building platforms that can be deployed in clusters on premises that will support both HPC and AI class of workloads.
Fascinating.
And so, yes, AI is a first-class citizen in the processing world, in our view.
That's great to hear. So another thing that I wanted to touch upon really quickly before we open up for questions. So IBM Power AI is something that's fascinated me for a long time. Hard ID models, all of these different things that I work on, a lot of them are trained on IBM Power Systems. One of the main reasons I use Power Systems, of course, apart from like the high core and thread count, is simply the fact of the very, very high bandwidth interconnect between the CPU and the GPU in terms of memory. Yep. So what are your views generally on IBM Power Systems and how they differentiate themselves from other solutions in the market?
Yeah, I think that you hit the nail on the head with that. Those systems were very purposefully architected to unlock bandwidth between CPU, GPU, and memory for a set of applications. And so they do very well. And what that means is if that's your core workload, you want to purchase a machine or purchase time on a machine that will produce the result the fastest and most cost effectively. So I think that and again, is evidenced by the fact that in state of the art right now, the top supercomputers in the world are running that type of technology. Yes. And clearly across, no matter what CPU architecture you use, that is one of the problems, right? Is bandwidth, between chips and devices, and the interconnect between those. And there's, I think, still raging debates about what those look like. Now, we happen to use InfiniBand for our internode communication to have low latency capabilities. There's a lot of research going on into using, again, in traditional supercomputing, there's all sorts of custom fabrics, but obviously in cloud, you want to have a standard, and today's biggest standard is Ethernet. But how do you then take some of the challenges with Ethernet and get to low latency interconnect? So these are challenges that the industry as a whole are trying to tackle. And what we've done is taken the types of infrastructure that have served the purpose-built community really well and applied those in our cloud.
That's great to hear. Wonderful. Thank you very much for sharing your thoughts. But now, if you have any questions, we would love to hear them. Simply raise your hand. We'll get a microphone to you so we can hear you, and people on the live stream can hear you as well. And we will answer your question. If there are any interesting questions from the live stream, feel free to let me know, and we can go ahead and answer those as well. If not, then I've got a few more things that I already got on social media, even before the episode started, that we can go through as well. Yes. If not, then I can repeat it, but hopefully it works.
Okay. There are a couple from the live stream. So you got some nice compliments about your data science work, and some people are wondering what you recommend for their data science learning and what kind of courses or approaches they should take.
Sure. So in terms of data science learning, I want to get your thoughts on that too, but really quickly, one thing that I do want to say is, first of all, in terms of learning about data science, machine learning technology, I actually work with the team here at IBM, the Skills Network team, and so there is a website that you can go to, cognitiveclass.ai. They provide free courses on a bunch of different topics, all the way from like programming in Python generically, all the way to data science and machine learning technology, really example-driven learning. So it's really fun stuff that they do. I've actually written a course on Swift for TensorFlow on a bunch of different machine learning algorithms that you can implement with it. So I would definitely recommend taking a look at Cognitive Class. They provide labs, kind of like Google Colab, where you get free access to things like GPUs, Power AI machines, a bunch of different stuff. Apart from that, this also reminds me, and this is actually tying into another question that we got on social media, about education. Quick question for you, Steve. Does Nimbix help out educational institutions? Do you enable them to work with your HPC cloud? What's the sort of dynamic like there?
Yeah, we do. We actually work and collaborate with educational institutions around the world, universities, and even done some high school, support work.
Very nice.
We offer educational discounts for our compute infrastructure for just kind of mainstream usage, but we also offer sponsorship programs for qualifying projects. So if you have projects, whether it's in data science, deep learning, or in traditional high-performance computing, we have a form on our website you can fill out, and then our team actually takes that, and we'll get in touch with you about whether or not the projects qualify.
That's great to hear. Wonderful. All right, so I hope that answered your question. I do believe we have a question from the lab. Yes.
Hello. Okay. So I have a question regarding networking. So you mentioned that. So I know that high performance computing, the state of the art to interconnect between different compute nodes is InfiniBand. But I was wondering if you guys at Nimbix tackled the problem of, let's say, cross-regional computing, where for example you have a computing facility in Houston, and you want to expand it to Toronto.
Yes.
So how would you approach this? Is it possible? What are your comments?
Sure. So there's a couple things. One is there are some technologies, but they're I would say they're definitely not mainstream, where they've looked at trying to reduce latency across large distances for a sort of a multi-scaled out distributed computing task. However, I would say that for most distributed computing tasks, you will want to run those in a single data center. But to tackle the issue of spanning regions, we actually introduced our platform technology. We call it Jarvis XE. And it's basically using our cloud technology, but deploying it at other compute centers, whether it's your own data center in a different region or on another public cloud. And what that provides is the same API, the same processing environment, the same application stack, and it allows those to synchronize seamlessly across those endpoints to be able to do your computing. You still have the challenge of obviously data locale. So, because data movement can still be an issue, you have to get your data to where the compute is, or your compute to where the data is. And so if you have a data center with a data lake and you have compute there, we would layer in Jarvis XE that allows the workloads to span those different regions.
Wonderful. More questions in the air here? Live stream?
There are a couple more. So do you think quantum computing will make HPC clusters obsolete?
Do you want? I guess I'll quickly share my thoughts on that first. So the thing about quantum computing is I would say that it's difficult to say exactly what kind of impact it will have on the future of computing. And I say that in the sense of it most certainly will help us with a lot of different things. Like there's some use cases that are very, very particularly suited for the kind of computing that quantum computing provides us with. But I feel like quantum computing isn't as general purpose as a lot of people make it out to be. It's not a faster computer. It's not a better computer. It's a different kind of computer altogether, right? So there are some tasks, things like molecular dynamics, drug discovery, these kinds of things are naturally well suited for quantum computers. Whereas I believe things like artificial intelligence, machine learning, some certain components of it are. Like, for example, I believe IBM Research has, if I'm remembering correctly, actually a notebook that you can run now around training a component of like a support vector machine on a quantum computer, and it's great. But as of today, with today's technology, it's slower and less precise, and much more expensive. And so, as of today, not much. And in the future, I don't think it will make HPC clusters obsolete. But I do believe some tasks will be offloaded from traditional HPC environments onto quantum computers because of the fact that they are architecturally more well suited to those tasks. But what are your thoughts?
I agree with you completely. I think it does a different type of math very, very, it takes advantage of, quantum effects to do this type of math that a traditional computing system would not be able to compute in a reasonable amount of time. But for exactly the reasons Tanmay said, it does not displace the current types of compute that we do. Now, fast forward 50 years from now, it's, we'll see. There's going to be a lot of different technologies that coexist at that time, but I don't think we're in any danger anytime soon of making traditional clusters obsolete.
Has Nimbix been in touch with IBM Research
We
to get
have.
quantum
We have.
machines
We
yet?
actually we work with a few different quantum companies, both in because by the way, to build quantum computers, you need HPC to actually simulate what these qubits are going to do. So
Exceptional.
and then also quantum simulators
Yes.
can tend to take you can simulate on traditional CPU type farms, which, by the way, helps with code development. So for developers of quantum computers, using quantum simulators is a great tool.
Very nice.
Okay, so this is a bit of a related question, but someone on the chat is asking, what is the vision of HPC in the next 5 to 10 years from now?
I have my own view on this. I think that obviously there's two vectors. I think that so let's take a 5-year horizon. I think we're going to continue to iterate over the next 5 years in what I would call a traditional context, where we're going to, applications are going to continue to evolve and traditional Linux clusters. But I think the addition of AI and all of the technology and machine learning that's being applied in different areas is increasingly being applied to HPC, both in the types of solvers that we've done solving traditional types of problems, but also for the computing infrastructure itself. And so what I often talk about is this notion of, we talk about autonomous vehicles and autonomous cars. Why not autonomous computing? Let's have the machines, let's give the machines the tools. After all, if you process, billions of hours of compute, you've got a lot of data for what types of compute work really well to solve certain types of problems. Allow the machines to, use, experts like Tanmay to create capabilities that allow us to process faster. So I do think we're going to see what maybe we call it augmented HPC, right? AI augmented, where you're seeing the fusion of those things together and it reinforcing traditional HPC techniques.
That's fascinating to hear about, and to sort of add onto that, around like if I remember correctly, around 2 years ago, at the IBM Research Lab in India, before Watson Studio was a thing, when it was like a DSX, when the Watson Studio was released, they released a neural network modeler feature with it. And before neural network modeler was integrated in Watson Studio, it was called Jarvis, which is an acronym for something. And Jarvis was essentially the neural network modeler, but built with the Node-RED sort of connection interface. And one of the things that they did was, hey, if there's like a pattern of like neural network layers that we think could be arranged in a better way, they will actually use a machine learning model to say, hey, you could have a better block of layers here instead of this other block of layers, right? So they've been doing a lot of stuff, and as we see like AI, HPC sort of converging, I mean, as we were mentioning a little bit ago, that's going to be really, really useful, not in just terms of like software, but even hardware. When you have that AI model, what kinds of compute are best for it, right? So that would be interesting.
Yeah, no, and I do have actually one other thought on the kind of the next 5 years that I think is worth just talking about, and that's the idea of software development. To your point. And the ability, when we talk about heterogeneous architectures, things like new types of hardware, FPGAs being one, different types of ASICs that do purpose-built tasks. One of the challenges of any new infrastructure is, okay, if you build this very incredible machine, but you have no software that's compatible with it or runs on it, you can't do useful work. And so one of the things I do see evolving over the next 5 years is the methodologies, the continuous development and integration of software in concert with the release of new infrastructure capabilities, whether they be in the cloud or in OEM hardware that's released to be deployed on premises.
Fascinating. Thank you, Steve. More questions? Anyone in the amphitheater, raise your hand. We'll get it to you. But yeah, go ahead.
Okay, yeah, there are a couple more from the chat. So what is your favorite IoT use case being developed by a client on the Nimbix cloud?
I think we have a customer at Oregon State University that collects data on a ship out at sea. And they actually are applying, machine learning and deep learning, techniques. But they have actually the task of collecting this data at the edge, the edge being out on a ship in the ocean, and then actually bringing that data back to process and then, do their science on that. So I think that's one that's at least I'm familiar with. It's not what we normally think of when we think of IoT, but it's these places at the edge that we need to process, and we need to be able to have that data flow and give the processing capability to get the answers that they're looking for. Mm-hmm.
Okay, so there's a couple questions about use cases for AI. So somebody's asking, can we use AI to detect a lie using body language and brain activity? And also, can it be used to understand animal sounds and in different languages? So I don't know if you want to address those kind of together, but
that might be a bit more your.
So here this isn't directly tied to HPC, but that's fine. We can talk about AI a bit. So to answer the first question about lie detection, so there are certain subconscious patterns subconscious sort of features or signals that people do give off when they lie or when they do something that can be used in order to make a decision as to, hey, were you truthful or not? Now, what exactly those patterns are, how effective they are, and how good someone is at actually masking them, that's up for debate. That depends on the individual. That depends on a lot of different factors. For a long time, I've been working on this project around understanding electroencephalogram. And if you take a look, Microsoft Azure, one of their developer advocates had a talk, this was many years ago, where she took a lot of electroencephalogram data from her husband of when he was lying and when he wasn't lying, and tried to build a machine learning model to predict when he was lying. And it was moderately successful. Remember, though, that the human brain is like the most complex thing that we know of. And understanding even the most simple patterns from it can be incredibly challenging. So in theory, yes, the individual building blocks are there. We do pose estimation for body language. We can use recurrent neural networks to understand brain data. We can understand all sorts of different kinds of individual data with neural nets and make sense of it. But then from there, being able to take the actual data of, hey, was someone lying? What does it mean to lie in the first place? Is that relative at all? Like there's so many little things to work on there that it kind of depends, is what I would say. It depends on your use case. It depends on how broadly or how narrowly you want to define that use case in its scope. But to answer the second question about animal sounds, yes, very much so it is possible to do that. Many researchers have actually already done so. They took sounds from mice, for example, and tried to decode that into different things that they, I guess you could say, for lack of a better word, meant. But yes, it is possible. Once again, it depends on that scope. What do you want to do after deciphering that sound? What kind of classes do you want to categorize them into? So yes, it is possible because a pattern recognition technology exists. What patterns you want to identify, though, that would be up to your specific use case. Anything to add on that?
No, that was well said.
Okay, there's a question about quantum. Do you want to get into that? Okay. So somebody on the chat here would like to know about the current status of architecture in quantum computing.
So do you want to start off first?
I mean, I would not characterize myself as an expert on that. If you want to lead off, you may even be more familiar than me.
Sure. So I feel like right now there's a major problem with the world of quantum computing, and it's that it's not that we don't have enough qubits, right? That's definitely not the issue. We've got machines with 50 qubits. That's totally fine. The current biggest problem would be the topology of quantum computers, the interconnect between different qubits and how they can actually interact with each other, and also the fact that our error rates are astonishingly high right now. So quantum volume is low, even though the individual qubit count or the individual error count may be low or high, but the quantum volume is low. That's IBM Research's metric for calculating how good a quantum computer is. So I feel like we have a few major problems to overcome. First of all, can we put more qubits into a quantum computer and actually have them interact with each other? Because the circuitry for actually having them interact with each other has to be built manually. So the fact that we can actually have 50 qubits that can all interact with each other, that would be incredibly powerful. But not only just that, we've got to make sure that they are actually robust enough so that we're not losing information across every single individual gate that we put on the quantum computer. I mean, today you could run a simple Grover's algorithm and you wouldn't even get, a result that looks as if it's correct because the error rate is so high, you're just going to get random output. So it's really only useful today for, hey, let's put something in superposition, entangle two qubits, and try and measure them. So I feel like we need to increase quantum volume. And in terms of architecture, we need better interconnect between individual qubits. What do you think?
Yeah, I think what I was going to say is I think error rate was what came to mind, and I think the other thing is just state of use case and software. And I think I would say I would still characterize it. I agree with you. We have a lot of qubits in terms of density of qubits, but it's really the application of the machines and the use cases. And I think that there's a lot of very specific niche use cases where they're again very well suited. But I think it's the idea of them becoming pervasive. Those use cases need to present themselves, and we need to have more developers, actually thinking about how to leverage capabilities that are unique to a quantum computer.
Absolutely. And one more thing that I want to mention is that quantum is fundamentally unintuitive. We live in a classical world, and our brains don't work in a quantum way. I mean, it pretty much, if you were here for the first episode of TechTime, Rob, Sam, and I, we were talking about how artificial intelligence can pose a sort of illusion to our mind down to an innate or a subconscious level. And away from the field of AI and the field of quantum, we have something similar. I actually personally think that it's easier to develop with quantum computers if you forget what you've learned about classical computers altogether, because it's fundamentally entirely different, not just from an architectural standpoint, but from a physical standpoint, it is fundamentally different. And so what I'm trying to say is, the tooling around quantum computers is also in its infancy. For example, IBM's quantum assembly language, it doesn't have a great optimizer yet, which is definitely an issue. Because if you write a quantum circuit that uses qubit interactions that aren't compatible right now, then the optimizer, the interpreter technically, is responsible for taking that quantum assembly and actually compiling it down into something that works, but then also making it more efficient. And in order to think in a way where developers can think in this like quantum world and work on compiler optimizations for quantum computers, that's something that requires a lot of effort. So compilers are what a lot of technology really boils back down to. Even in quantum, we need better quantum compilers if we want to be able to leverage quantum computers better.
Okay, thank you. So there's a few more here in the chat, but we maybe just have time for one more.
Sure.
Okay.
Let's get one.
Are there any regulatory and compliance concerns when it comes to using HPC?
Yes, there are in different organizations, different countries, there are different compliance requirements, and that ranges from even compliance requirements within a given enterprise. So certain global firms have their own regulatory sort of self-imposed requirements, data security and IT security postures. Regions and countries and governments have their own posture. In some cases, the data sets required to do computation on may not be allowed to leave certain regions. And so it's important for users to understand if they are subject to some of those regulations based on the application area, to be aware of that. And I think the other thing is just, again, around the types of applications. There are obviously applications in high performance computing that are, sensitive, and so they can be regulated.
Okay, great. Thanks a lot.
Thank you very much. All right, so unfortunately, that concludes today's episode of Tech Time with Tanmay. Thank you very much, Steve, for
It's great to
joining
be
once
here.
again.
Yep.
Thank you very much. It was an honor. Thank you. Thank you very much for joining. Thank you.